In this lecture, we're going to finally introduce interactions. As soon as we include interactions, we can no longer solve the theory as we could when we didn't have interactions in the free theory. So let's look at a simple example. If we have a scalar field theory with a Lagrangian, a kinetic term, and a mass term, that's all that we had before, but now we'll add a new term to the interaction proportional to, let's say, 4 powers of the field. Okay, we'll see later on why that particular choice is interesting, but just think of it as a random choice. Now, when lambda was 0, one way to think about the fact that we could solve the theory is that we could write the most general solution to the Heisenberg equations of motion, the most general operator solution. But now, with lambda there, the Heisenberg equations of motion become box plus m squared phi is not 0, but it's rather minus lambda over 3 factorial phi cubed. It's now a nonlinear equation. The general solution is not known. Okay? So, of course, we need to consider interactions. We need to consider particle interactions. And almost everything that we know about quantum field theory, interacting quantum field theory, comes from treating interaction terms like this perturbatively. Okay? So that's what we're going to be spending the entire course actually on. There are some non-perturbative things known, but it's a very incomplete subject. So what is the basic idea? The basic idea is that, well, to 0th order in lambda, phi is a free field, right? So we can think of phi of x as being given by a free field as before, and we know how to solve the Heisenberg equation of motion, right? So we write it as a free field, just as before. So this is a real scalar field, okay? This is a free field. And now the mistake that we have made is order lambda. And we can try to iterate this equation to sort of include the higher order lambda terms. Now if we look at the interaction Hamiltonian for this, this is d cubed x, right, times lambda over 4 factorial phi to the 4th. That's the, okay? And now if we just plug in this expansion here, where phi is free field plus higher orders, then what we get is, dropping a lot of factors, we get a power of lambda here, okay? And then to leading order, this phi is just a free field, so it can be written as free field annihilation and creation operators to the 4th, and the mistake I've made is order lambda squared, right? Okay? So if I multiply this out, I have lambda, I'll get alpha to the 4th terms, alpha cubed, alpha dagger terms, alpha squared, alpha dagger squared terms, alpha dagger cubed terms, alpha dagger to the 4th terms. I get a bunch of terms with any numbers of alphas and alpha daggers that total 4. Okay? Now let me just pick on one particular term here, the term with 2 alphas and 2 alpha daggers. Okay? Now what does this term do? Well, we think of this interaction term as acting on the unperturbed space of states, right? So in general, in quantum mechanics, if we do perturbation theory, we have some Hamiltonian that we can solve, and we have a set of eigenstates for that. And then the perturbation Hamiltonian gives rise to transitions among the unperturbed states, okay? So we think of the perturbation Hamiltonian here as giving rise to transitions among the unperturbed states, and we calculate those probabilities by inserting powers of the perturbation Hamiltonian, which is this thing right here, okay? So when we insert powers of this between free particle states, this term right here does something that we can recognize. Namely, what this term will do is it will annihilate 2 particles and create 2 particles back again. But there's actually a sum over momenta here, and so it doesn't necessarily give you back the same momenta that you had. In other words, this is scattering. 2 particles in, 2 particles out, okay? So this term right here at this leading order lambda already does something that we would recognize as a particle interaction if we insert this into free particle states, okay? Now it's a lot less clear what the role of these other terms is, okay? But I just wanted to get across here right now, I just want to get across the basic idea that the interaction Hamiltonian gives rise to transitions between states, and that includes scattering, okay? All right? So in fact, scattering is the main physical observable that we have, it's the main handle that we have on relativistic particle interactions. It's incredibly important both experimentally and in fact conceptually the way that we think of the entire theory. Okay, so let me remind you, let's review a few basic facts about scattering in quantum mechanics. So what is the basic setup for scattering? Well, the initial states that we have some initial states. So I'm drawing one of these diagrams here where time is running up, okay? So the initial states from a scattering experiment are wave packets, okay? And these wave packets are wave packets of single particle states. So there's one particle here localized in a wave packet. So it will have there'll be some position uncertainty delta x and some momentum certainty which will be 1 over delta x for this wave packet. And we'll assume that all the initial wave packets have the same width, the same position space width and the same, therefore, momentum space width, okay? Now, if you're an experimentalist and you want to specify the momentum very, very accurately, you're going to have to use larger and larger wave packets. But for any given accuracy that you want for your momentum, you can always make the wave packets initially separated by a distance L, which is much, much bigger than delta x. Okay? So by making L big enough, you can get an arbitrarily large accuracy on the initial momenta of these different wave packets. Okay? So these wave packets have some quasi-well-defined position and momenta consistent with the uncertainty principle, and then the experimentalist aims these wave packets, okay, so that in the future, if you propagate them forward in time, there will be a region where they overlap, okay? The wave packets overlap, and therefore they interact, okay? And then when they interact, what do we expect to happen? What we expect to happen is that they scatter, okay? And so what will happen is that lots of complicated things may happen here. Particles may be created. That's, for example, what happens in collider experiments. Many, many particles are created. But no matter how complicated things are here, the assumption is that all these particles will eventually stream out. And so if we wait long enough in the future, all of these particles, again, will be isolated single particles that don't interact. Okay? So that's the basic setup for scattering. And what this tells us, the bottom line is that it tells us that in scattering experiments, the particles do not interact at very early times or at asymptotically late times. Okay? That's the important feature of scattering experiments. Okay? So we want to we want to build this assumption into our theory of scattering, that the particles become non-interacting at early and late times. And so what we're going to say, we're going to assert, is that our Heisenberg fields, phi of x, okay, become free fields. They become free fields as time goes to plus and minus infinity. Okay? All right. Now, you would notice that this is not something that I have derived. I've just asserted it. And this illustrates something about the way physics works, right? Mathematicians always want to derive everything from some set of assumptions. In physics, we're most often interested in testing the assumptions. So we make assumptions, we try to work out what the consequences are. If they don't work, we hit a brick wall and we figure out what went wrong and modify the assumptions. And that actually turns out to be the case here. If we follow this thing through, we will find later on that there are problems with this assumption in the cases where the theory has massless particles. okay? But for now, we're just going to go full steam ahead, and we will try to understand those problems when we get to them. Actually, not in this quarter, so anyway, but that will happen. Okay, so, but even this is not quite the precise conjecture. More precisely, what the conjecture actually is, the claim is that this thing, as if we go, let's say, to the far past, we get a factor of root z times an in-field, okay? So this is as t goes to minus infinity. So in the far past, the fields approach not free fields, not canonically normal. This is a canonically normalized free field, but a factor times free fields, okay? And the same factor times some free out fields, okay, when t goes to plus infinity, okay? So when I say free fields, in general, I should allow some factor like this. Now, why shouldn't that factor just be 1, okay? First of all, just to emphasize the meaning of this factor, what I mean is that, for example, the fields are completely canonically normalized fields of the type that we've been talking about, okay? So we have, for example, our usual formula for the free in-fields in terms of creation and annihilation operators, and these satisfy the canonical commutation relations. Okay, so between two in-fields, in creation and annihilation operators, alpha and alpha dagger. This is our usual Lorentz invariant delta function, et cetera, et cetera. So we're normalizing these guys canonically, but who said, when these guys become free, who said that they become canonically normalized fields at t equals plus and minus infinity? Okay, well, in general they won't, okay? And in fact, it's not, they really won't, they actually don't, and the reason is, the way you can understand that is if you take this canonically normalized in-field, okay, at say x, acting on the vacuum, right, then that will be equal to dp e to the, I guess, plus I p dot x p, right? Just because only the creation operator piece matters for this, right? But now if we take this interacting field acting on the vacuum, it will create not just a one particle state in general, it will create many particle states, okay? And so it will create, part of what it will create will be what we have for the one particle states like I have here, but there are other states that it can create, right? That's what makes it an interacting field, okay? And so the fact that there are other states here is reflected in the fact that this square root z, in fact, turns out to be less than 1, okay? You can show, this is not, I don't think we're going to do that, we're not going to do this quarter, that this square root z is actually strictly less than 1 as a consequence of unitarity, essentially, okay? So eventually, if you go on in quantum field theory, you know that z is 1 plus perturbative corrections, because of course if I set my coupling to 0, if I set my interactions to 0, then z is 1, because I just have a free field. And you can compute z in perturbation theory, and you would learn how to do that in your subsequent course. But one thing to realize is, right away, is that since the z is a multiplicative correction that starts out as 1, these terms here always give you subleading corrections, okay? So in this quarter, we're only going to be computing the leading contributions to scattering and decay processes, physical processes, and so we can actually just set z equal to 1, as long as we're looking at just the leading contributions to some process in perturbation theory. Okay? Okay, good. Okay, so so with this setup, how do we actually do this perturbation expansion? How do we actually expand in this these powers of lambda in a practical way? So to do that, it turns out to be useful to use not Heisenberg picture, not Schrodinger picture, but interaction picture. So we use yet a third picture for the fields, okay? So let me explain it and then explain why this is so useful, okay? So let's start back in Schrodinger picture, our old friend. In Schrodinger picture, the states evolve with time, right? And so now we can say that the state at time t is related to the state at some other arbitrary time t naught by some time evolution operator, okay, with the state at t0, okay? And of course, the operators are time independent, okay? Now, for Heisenberg picture or any other picture, what we're going to do is we're going to assume that the pictures agree at t equals t0. So t0 is just an arbitrary parameter. It's the time at which the various pictures will agree, and it's useful to have that as an additional parameter. So here now, what we're doing is we're going to take, the Heisenberg state, which does not evolve in time. The idea is that we take out all the time evolution from the states. So we define that to be e to the plus I h t minus t naught times the Schrodinger state, right? And so when we do that, this thing just gives me the Schrodinger state at t naught, okay, which doesn't depend on t, okay? But then to keep the matrix elements the same, the price we pay is that the operators have to be time dependent, and we can see that to make the matrix elements the same, what we want is an IH t minus t naught times the Schrodinger picture operators e to the minus IH t minus t naught. Okay? All right? So that was just Schrodinger picture, Heisenberg picture, just with the agreeing at a time t equals t naught. Now we want to introduce the interaction picture, sometimes also called the Dirac picture, because Dirac introduced it. And in the interaction picture, both the states and the operators depend on time. And the splitting is defined by the fact that the full Hamiltonian will be given by some leading order Hamiltonian, which I'm imagining I can solve exactly. I can solve this problem. If this were the whole Hamiltonian, I could solve it exactly. And then I have some interaction term, okay, which in practical applications I'm going to treat perturbatively as a small perturbation, okay. So in our case, this is free field theory. This is the interaction term, okay. And the idea in interaction picture is that rather than taking all of the time evolution out of the states, we take out of the states only the time evolution due to h naught, okay. So we'll define the states in interaction picture, which do depend on time, to be the e to the plus I h naught t minus t naught times the Schrodinger picture states. Okay? And then to keep the operator matrix elements the same, the interaction picture operator has got to be conjugated in the compatible way. Of Schrodinger, e to the minus I h naught t minus t naught. Okay? Okay. All right? Okay. So that's interaction picture. Now let's work out some basic properties of it, and when we get those properties, we'll be able to see why it is useful. Okay? So what we're going to do is we're going to define the interaction picture time evolution operator. So we have our state, time-dependent state in the interaction picture is defined to be a unitary operator, okay, acting on the initial state, the state at time t equals 0. Okay, so this is implementing the time evolution, okay, in interaction picture, and it's got to be unitary, and it is, okay, because if you look at the formulas that I had before, okay, actually what is this? This thing right here is e to the plus I h naught t minus t naught of the Schrodinger picture, Schrodinger picture state at time t. That was just the definition. But now this thing right here, okay, is e to the minus I h, the total h, t minus t naught times the Schrodinger picture state at t0, okay? But the Schrodinger picture state at t0 is the interaction picture state at t0 by definition. That's the definition of t naught. And so from this, what I see is that the interaction picture time evolution operator is just this product, e to the plus I h naught t minus t naught e to the minus I h, the total h, t minus t naught. Okay? So there's a time evolution operator in interaction picture, and it's easy to see that it's unitary because it's the product of unitary operators. The product of unitary operators is always unitary. Okay? So now we see why interaction picture is useful for a scattering experiment. Because in a scattering experiment, we argued that the time evolution is free at early and late times. That means it's governed by h naught, okay? And that means that, in fact, the interaction picture state, okay, becomes time independent, okay, as t goes to plus and minus infinity, right? Interaction picture takes out the time evolution of the due to the free part of the theory, and at early and late times, that's all there is, and so these interaction picture states become time independent, okay? So that means that we can define the evolution operator from early times to late times. We can take the interaction picture evolution operator to some final time from some initial time, right? In quantum mechanics, typographically, time always goes from right to left. And we can take the limit as t initial goes to minus infinity, t final goes to plus infinity, and the point is that this limit exists. The states stop evolving in time at early and late time, so this thing settles down, okay? And this is the definition of what is called the S matrix, okay? So the S matrix tells us the probability to have a transition between different interaction picture states, and these interaction picture states are defined to have the free time evolution, the sort of trivial time evolution that we've been studying up till now, that is taken out of the states, okay? And so we can relate this directly to physical observables because the probability to make a transition from some initial state to some final state, right, will then just be proportional to the matrix elements between this S matrix operator squared, because probabilities are squared in quantum mechanics. Okay? So this S matrix is the basic object that we want to study if we want to study scattering. Okay? Okay, so what we want to do then is we want to learn how to compute the S matrix, okay, in perturbation theory, and then we want to know how to interpret it, how to actually get physical results out of squaring it, and so on. So we're going to do that for a simple example in this lecture, okay? So the first step is we need to compute the S matrix, okay? And we already have an expression for the S matrix, right? But we need a new expression, okay? This expression that we have is not Lorentz invariant at all, so the first step is we're going to derive a new and improved expression for the S matrix. So the S matrix is really just the time evolution operator in interaction picture, and with the formula that we have for this is that this is I h naught t minus t naught e to the minus I h t minus t naught, right? That's the formula that we have. And yeah, this formula doesn't look very symmetric or very pretty, let alone Lorentz invariant. So we're going to get a new expression for this, and the strategy is going to be to write a differential equation for this object and then solve it. That seems like a rather roundabout way of doing things, but well, let's do it this way, okay? So we're going to get a differential equation by differentiating this thing with respect to t, okay? All right? So let's do that using this thing right here. So the t differential hits these two terms right here. When it hits this term right here, it pulls down a factor of I h naught, okay? Now, h naught commutes with itself, so this is some series in h naught. So I can put the I h naught in front, I can put the I h naught on this side, it makes no difference. My mood is that I want to put it on the right side, so I'll put it on the right side. Okay, so I have I h naught, t minus t naught. When this derivative hits this t, I get a factor of I h naught on this side, and then I still have this thing here, minus I h t minus t naught. Then I have a term where this time derivative hits this t, that gives me a factor of minus I h. I can put it on the left here or on the right here. I'm going to put it on the left here, okay? So I get an e to the I h naught t minus t naught, this first term here, then I get a minus I h, which I'm putting on the left, e to the minus I h t minus t naught, okay? And the reason I put them on those sides there is now I can combine these two things together because I have the same thing on the outside, and I have an h naught minus h. That actually gives me the interaction term, right? So I have e to the I h naught, t minus t naught, and then I have an I guess I would have a minus I h interaction, e to the minus I h t minus t naught. Okay? Now what I do is I'm going to insert here a factor of e to the minus I h naught t minus t naught e to the plus I h naught t minus t naught. Can't stop me from doing that. That's one. And then when I recognize this first thing, this times this times this, is precisely the interaction picture version of this operator right here, okay? So this is then going to give me what I'll call h sub capital I, okay, which does depend on time, right? This. And then what I have left over is this times this, okay? But that is precisely the ui of t comma t naught, okay? And then there's this minus I, which I almost forgot, but there it is, okay? So this is what, so I've actually derived a kind of nice looking equation here, which actually is a Schrodinger equation for this ui right here. And just to be clear, this h sub I t is e to the I h naught t minus t naught, the interaction picture guy in Schrodinger picture, right, e to the minus I h naught t minus t naught, okay? All right, and so perhaps I should really call this thing h interaction in the interaction picture, but that's just too disgusting, so I'll just call it h sub I, okay? Okay, and so this is the differential equation we're supposed to solve, d by dt ui t of t naught, and it's a differential equation in t. T naught is just sort of going along for the ride, okay? And the initial condition that I want to impose, okay, you can see from this formula up here, my other formula, my bad old formula for ui, you can see that ui of, if I set t equal to t naught, so I have t naught, then this is 0, this is 0, I just get 1. So this is my initial condition, okay? So I have to solve this differential equation with this initial condition, okay? And we solve this by the time-honored method of writing down the answer, okay? The answer to this is called the Dyson Equation, because it was first written down by Dirac, but Dyson made it famous. He showed the utility of it for getting a Lorentz invariant expression for quantum field theory amplitudes. Okay, so the solution is ui t naught is equal to the time-ordered exponential minus I integral from t naught to t dt prime hi t prime. Okay? Now what in the world does this mean? This time-ordered exponential is the following thing. Okay? What this means right here is, remember when we take an exponential of an operator, it's defined by its power series. So similarly, this time-ordered exponential is really defined by its power series. So we have sum from n equals 0 to infinity, and we have minus I to the n over n factorial, okay? And then if this was an ordinary exponential, we would just have n powers of this thing up here, right? So what we actually have in the time-ordered exponential is almost that. We have t0 to t dt1, so we just have n of these integrals, dtn. And now if this was an ordinary exponential, we would just have here hi t1 through hi tn, right? This is what it would be if we wanted an ordinary exponential. What makes this a time-ordered exponential is that we have a time ordering operator that acts on this product. Okay? This is called a time-ordered product. All right? Now the time-ordered product is just what it sounds like. So if I have two operators, O1 at T1, O2 of T2, then what this is if T1 is bigger than T2, okay, if T1 is bigger than T2, this is just O1, T1, O2, T2. If T1 is less than T2, okay, then I reverse the two. It's O2, T2, O1, T1. Okay? And so the way to remember the rule is that it's later to the left. Okay? So what we do is we put the latest operator to the left. Yet another example, as I said, in quantum mechanics, time is always flowing from right to left. Okay? And when you have more operators, it's just the same thing. You put the operators in time order just by brute force. This is the definition. Okay? So this at first doesn't look terribly natural. It turns out it's a lot more natural than you might think. It had this time ordering will be with us for the rest of it's throughout quantum field theory. Okay, so let's just some elementary but important properties of the time ordering operator is that clearly. Clearly, the order of things inside time ordering doesn't matter, because time ordering just puts them in the time order. So if you write it this way or this way, it doesn't matter, right? Another thing is that if we have a product of Hermitian of Hermitian operators, this thing is Hermitian. Okay, that'll be important for us. That if we will be interested in Hermitian operators, time-ordered products of Hermitian operators are again Hermitian. Okay, if that's not clear to you, write out the definition and you will see. Okay. Okay, so I asserted that this time-ordered exponential solves this equation. Let's check. Okay. So we want to take, let me erase all this. We want to take d by dt of this time-ordered exponential, okay, of minus I integral t naught to t dt primed h t prime, okay? And sorry, I shouldn't have written this out. Let's just write out the sum, which is the actual thing that it is. This is n equals 0 to infinity minus I to the n factorial. Then we have these integrals all going from t naught to t, dt1, dtn, all going from t naught to t, time order product of hi t1, hi tn. Okay? Okay, so what does this time derivative do? It hits each of these times that are here on the limits of integration, right? These integration variables are just dummy variables. And so what happens? Well, we're going to get n terms, because there's n, well, for each of these guys right here, n equals 0 to infinity minus I to the n over n factorial. For each of these, we will get n terms. Good. So let's write the first term that we get. Okay? So the first term that we get hits this guy, and so it leaves the remaining integrals, so there'll still be a d2 up to dtn, so there'll be n minus 1 integrals, all still going from t0 to t. Okay? And then it hits this guy right here, okay? And, sorry, and then, so that's all it does, it just erases that guy right there, okay? And then it just leaves everything the way, the inside of this thing exactly the way it is, HITN. Okay, except, sorry, that the first thing now, T1, is evaluated at T, where I hit this integral here. So I have HI of T, and then I have my HI of T2, HI of Tn, okay, all inside the time-ordered product, okay? But now, this is where the magic of the time ordering comes in, because if I didn't have the time ordering, I could still write this product right here, okay? But the time ordering tells me that, you see, t is always bigger than t2 through tn, because the integral just goes up to t. And so the time ordering always forces this hi to be on the left, okay? Now that's not such a big deal for this term right here, because this term right here, hi, is already on the left. But the next term, you see, where this d by dt hits, say, t2, I would have hit1, and then I would have hit. But this time ordering always moves the latest guy to the left, so I can, okay, so here I have plus n minus 1 more terms, right? That's the point, okay? And for each of these n minus 1 terms, the hi of t term that I get gets moved to the left. So I can pull it all the way out. And so I can just get I can just get an n equals 0 to infinity minus I to the n over n factorial, and then I get my hi to the t, and I get n, exactly the same terms, okay, because each of those terms do the same thing. And then I have my leftover integrals t0 to t, dt2, dtn, t0. So all these terms now look like the first term, hi of tn. Okay? Now, if I stare at this a little while, I will see that this is indeed exactly minus I hi of t times the whole thing that I had before, the whole time-ordered exponential I had before, right? So the reason is that this n divided by n factorial gives me an n minus 1 factorial, okay? And actually, the n equals 0 term vanishes here because of this n. So this thing starts with n equals 1, but then there's an n minus 1 factorial, there's n minus 1 integrals, there's just an extra factor of minus I, and so this is what I get, okay? So that's the basic reason that I need this time ordering. The time ordering in this exponential allows me to pull the hi of t all the way to the left and makes this a true equation. Okay? Okay. All right, so that is Dyson's formula. Now, why is Dyson's formula any better than the previous expression that we had for the time evolution operator and interaction picture? So to see why it's better, let's write it out. So the S matrix now, the S matrix is just this time-ordered exponential where the initial time is minus infinity and the final time is plus infinity. So I just integrate over all times dt of my interaction Hamiltonian, okay? But what is my interaction Hamiltonian, okay? My interaction Hamiltonian is d3x, okay, times my interaction Lagrangian evaluated on the interaction picture fields. And there's a minus sign, okay, because this interaction term is just a potential term, so the interaction Hamiltonian is just d cubed x times the interaction Lagrangian density. So if I plug this into here, I see that I get a dt from here, a d cubed x from here. So this whole thing becomes the following beautiful formula: d4x L interaction evaluated on interaction picture fields. Okay? And this is an exceedingly beautiful formula because it is manifestly Lorentz invariant now, right? So these fields here are, this interaction Lagrangian integrated, Lagrangian density integrated over space-time is just a Lorentz invariant thing, and I'm doing this time-ordered exponential here, okay? The time-ordered exponential is Lorentz invariance because remember that fields commute at space-like separation. So at space-like separation, any kind of ordering doesn't matter, okay? But at time-like separations, the order matters, but the time order is then Lorentz invariant. So it's beautifully Lorentz invariant, and yeah, it's beautiful, so let's appreciate it, okay? Okay, so but then what we're going to do with this beautiful formula is we are just going to immediately start expanding it in powers of lambda, okay? So if we expand it in powers of lambda, the leading order term is 1. That's not very interesting. Then the next order term is I d4x, and then we'll have some minus lambda over 4 factorial phi to the 4th of x, right? And remember, these are interaction picture fields. What does the next term look like? It looks like I squared over 2 factorial, which is just 2. Then I have a d4x, d4y, and I have some factors minus lambda over 4 factorial. I get 2 factors like that. And then I have phi to the 4th of x, phi to the 4th of y, interaction picture, but they are now time ordered, right? And of course, then I'll have terms of order lambda cubed, just keeps going, okay? So the basic point is that what this does is it expands this S in powers of time-ordered products of fields, okay? So the basic objects that we'll be studying to understand the S matrix will be time-ordered products of fields, okay? Okay. So let's compute something. And to compute something, we need to have a theory. We need a model, okay? This is a toy model. It's not describing the real world, but it's a simple model that will allow us to do our first real calculation, okay? And we'll make it a little bit interesting, hopefully, okay? So we'll have a real scalar field, okay, which we'll call a meson, to make this thing sound like it's actually particle physics, okay? And it'll have a mass that we'll call capital M, okay? And then we'll also have psi, which is a complex scalar, okay? And we'll call that a nucleon. In the real world, nucleons are fermions, but in our toy world, they are scalars, okay? And it's a complex scalar. First of all, let me say this has mass, which I'll call little m. So these two different kinds of particles have different masses, okay? The complex scalar, there's going to be a U1 symmetry associated with that. So we'll have a U1 symmetry under which phi doesn't transform at all. Phi is neutral, okay? And psi transforms under this, okay? So in our toy world, we can think of this, there's a charge that's conserved by this U1, and we can think of that as baryon number. So we think of these nucleons as being baryons, even though they carry spin 0. Yeah, okay? This is our theory. So what is the Lagrangian, or the Lagrangian density? Well, we have the free field terms, so let me write it as a sum of a free field Lagrangian and interaction Lagrangian. The free field Lagrangian is the one that we always know. There is, it's capital M squared is the mass of our meson, and then we have d psi dagger d psi minus 1/2 m squared psi dagger psi. And here I'm using a bit of a shorthand here. I'm saying there's this is d mu phi dagger d mu psi, just a little bit of a shorthand. Okay, so this is just the sum of the free Lagrangians, okay? But now what is the interaction term? That's the important thing. The interaction term is going to be g phi psi dagger psi, okay? This is not the only interaction term I could write down. This is just a simple model, okay? All right, so there's our model, okay? Now, before we calculate anything, let's do a little bit of dimensional analysis on this theory, okay? So remember that we're using units where h bar and c are both 1, and so in these units, the only kind of dimensional quantity that we have is mass, okay? And so let's practice counting powers of mass. That's actually a very important thing, so let's just do it slowly. So the Hamiltonian is d cubed x times the Lagrangian. Sorry, times, let's look at the free Lagrangian, and let's look at the first term and the kinetic term like this, okay? So we know that if this is a Hamiltonian, right, it will have units of energy, which in our units are the same as mass. So we say that it has mass dimension plus 1. So remember what this means. This means that h has dimensions of mass to the first power. So when we say plus 1 here, we're talking about the power of mass right here, okay? And in our units x or t have dimensions minus 1. They have inverse dimensions of mass, okay? And therefore, our time derivative here has dimensions of plus 1 mass, not 1 over mass, right? Okay? And so then we can just match the dimensions right here. The powers of m have to add up to the same thing on both sides. So on this side, the mass dimension is 1. And on the right-hand side, we have 3 powers of minus 1 from the x's, right? We have x1, x2, x3. That gives me a minus 3 here. And then we have 2 powers of dt phi. And each dt phi has a dimension of plus 1 from t. And then we have phi, the mass dimension of phi, which I'll indicate like this, okay? And so we can just solve this equation right here. And what we find is that phi has mass dimension plus 1, okay? All right, and so yeah, you can easily check that. Usually we don't like. I started with the Hamiltonian because that's the thing. You will all agree that the dimensions of the Hamiltonian is energy, but it's actually more convenient to do things in terms of the action. Okay, so let's go back to the action. Right, if we write the action as d4x times L. Right, then what we realize, sorry, this is dt times L, which is d4x times script L. So this is the Lagrangian, this is Lagrangian density, the Lagrangian per unit volume, okay? What we'll realize is that the Lagrangian, not the Lagrangian density, and the Hamiltonian both have dimensions plus 1. That actually tells me that the Lagrangian density has to have dimension 4, right? Because, yeah, okay, right? Because the action is dimensionless, and then this thing, okay? So we learned that the action is dimensionless, okay, and the Lagrangian density has dimension 4. Okay, good. So then we can write down an equation just from the Lagrangian density looking like dt phi squared plus other terms. But from this, we can also just write down the equation that the dimension here is 4, the dimension here is twice times phi plus 1, right? Because there's 2 powers here. This has dimension 1, this has dimension phi. And again, of course, we get that phi has dimension 1. Okay? So at least when I do it in practice, this is how I do it. I just use the fact that the Lagrangian has dimension, Lagrangian density has dimension 4. Okay? Okay, so the field has dimension 1, big deal. What about our interaction term now? Okay, our interaction term is g phi dagger phi times phi. Okay, so using the same logic as here, the interaction term, of course, also has to have dimension 4, and it has dimension g, okay, whatever the dimension g is, plus 3. 1, 2, 3, okay? So what we learn is g has dimension plus 1, it has positive mass dimension, it has dimensions of mass, okay? All right? Now, why is that important? It's incredibly important because what we're doing here, what we're planning to do, is we're planning to do a perturbative expansion in powers of g. The lowest order expansion is just independent of g. Then we have terms of order g, g squared, g cubed, and so on, right? But g has a dimension. So if we're computing the corrections to some scattering amplitude, say, in powers of g, the corrections have to be powers of g divided by something with dimensions of mass, 2 powers, right? These are going to be positive powers, 1, 2, 3, and so on. And what is this E going to be? It has to be some energy scale associated with the scattering process of interest, right? And we'll, of course, do examples, but yeah, it has to be some characteristic energy scale in the process of interest. But this already tells us something very interesting. This tells us that this expansion is good for large E. Okay, at large energies it's good, right? Because if we just take the same scattering process, we go to higher and higher energies for the same G, we're making this expansion better and better. And conversely, it's bad, okay? This expansion breaks down for small e. Okay? So without even doing any calculation whatsoever, there's something fundamentally important just from the dimension of this interaction. And this type of interaction, which is very important at small energies but not important at high energies, is called relevant. Okay, why is it called relevant? Because it's relevant at small energies, what we call the infrared, low energies. Okay, all right. Okay, so all right, so let's actually do it. Okay, and so an incredibly important point, which I actually forgot to mention when we were first talking about the interaction picture. So let me go back. Let's go back to the interaction picture in general. And remember that the interaction picture operators, okay, were functions of time. And they look like e to the I, h naught, t minus t naught, times the Schrodinger operator, e to the minus I, h naught, t minus t naught. Okay, and so these interaction picture operators satisfy a Heisenberg-like equation of motion. If I just differentiate this thing right here, I find that d by dt of OI of t is equal to I, the commutator of h naught O of t in the interaction picture. Okay, so this is the same kind of equation of motion I wrote down for the Heisenberg picture, but now there is h naught appearing here, okay? So in other words, in interaction picture, the fields, they do have time evolution, but the only time evolution they have is the free time evolution, okay? So that's incredibly important because it means now that if we go to field theory, right, the interaction picture fields are free fields, okay? These are the things that we know all about, okay? So if you remember, we're going to be expanding now this time evolution operator in interaction picture, but it's written in terms of interaction picture fields, which are free, okay? And so that is what is going to be allowing us to actually do calculations, okay? And so in particular, right, remember that the interaction picture, okay, so now we have to ask, okay, where are we going to choose the interaction picture fields to agree with the Heisenberg picture fields and Schrodinger picture fields? That was the time t naught. So if we take t naught goes to minus infinity, right, then what we have is that the interaction picture fields, okay, they agree with the Heisenberg picture fields at time t equals minus infinity, okay? But at t equals minus infinity, the Heisenberg fields were square root g times these free in fields, okay? So that means that the interaction picture fields are this root z factor times free in fields once we just make this choice. Okay? Okay, we could also have used the out fields, but that's doesn't matter, but we'll use in fields. Okay? So what this means now is that we can write the interaction picture fields in terms of free fields. And for our discussion, I'm just going to set this factor of root z to 1. Okay? So like I said, that's the difference between root z and 1 only matters when we go to subleading processes, which we won't do. Okay? And I'm also going to start dropping the subscript I. We're going to be using interaction picture, but I'm not going to keep writing I all the time. So now, with that understanding, I can write my fields in our toy model, for example, the meson fields. They will be, I can write them in the usual way in terms of creation and annihilation operators. So we'll introduce some creation operator alpha, e to the minus I p dot x, plus permission conjugate, okay? And I will have my nucleon fields, okay? And this is a different kind of particle, and it has charge. So this will be some dp. So I have to introduce new kinds of creation and annihilation operators for my nucleon. I'll call this beta of p, e to the minus I p dot x, plus gamma dagger of p, e to the plus I p dot x. Okay? So I'm going to have 3 different kinds of creation and annihilation operators. And also, we have to remember that these 2 different particles have different mass. So to remind myself of that, this integral right here goes over the mass shell for the mesons, which have mass capital M. This is an integral over the mass shell of the nucleons, which have mass little m. Okay? So remember what this means. This shorthand here is d cubed p 2 pi cubed, and then I have this factor of 2, square root p squared plus m squared, right? So the mass is important here, okay? So yeah, remember that all of these are interaction picture fields, and this right here annihilates nucleons, which for example we can take to have charge plus 1. This thing creates antinucleons, which have charge minus 1. Okay? All right? Okay, so that's our basic setup. Now we're actually ready to compute something. Okay? And the simplest thing we can compute is a decay process. Okay? So the claim is that if the meson is heavier than twice the mass of the nucleons, then what we can have is the meson can decay to 2 nucleons. Okay, can decay to nucleon. Okay? All right? So we can ask about the rate for this process. How fast does it happen? That's a physical observable. Okay? So let's just try and do it. What is the initial state? The initial state will be alpha dagger p acting on 0, because alpha dagger creates a meson with momentum p. Okay, so that'll be our initial state. What is our final state? Our final state will consist of, the meson will go to a nucleon plus an antinucleon. Excuse me. Very important. Remember that charge is supposed to be conserved. The meson has 0 charge, the nucleon has charge plus 1, the antinucleon has charge minus 1. So we have to have a nucleon-antinucleon pair produced. Very important. Okay? And so our final state, therefore, will be what? It will be a nucleon plus an antinucleon. That will be B dagger of Q1, gamma dagger of Q2, acting on the vacuum, right? So beta and gamma daggers, respectively, create nucleons and antinucleons. Okay? So there's our initial state, there's our final state. Okay? Okay? And what are we supposed to do? What are we supposed to compute? What we're supposed to compute is the matrix element of the S matrix between the initial and final states. So the final state is gotten by acting with a beta dagger, so that becomes a beta when we put it on this side, and a gamma with momenta Q1 and Q2. Then we're supposed to be inserting this S matrix, which starts off as 1, plus I, G, then we have this D4X, we have this interaction term, psi dagger, psi, and phi, okay? And then of course we have higher order terms in G. And then we have the initial state over here, which is gotten by taking an alpha dagger of P acting on the vacuum state, okay? So we're just interested in the leading term, okay? So of course the leading term is this 1, but we know we're not supposed to get a decay when G is 0, right? So we don't expect to get anything from this term. But let's write it out anyway, because it'll teach us something. We need to understand exactly how it happens, that it doesn't give us anything. So we have a beta of Q, gamma of Q2, beta of Q1, gamma of Q2, alpha dagger of P, 0, and then we have the order G terms, okay? Now if we look at this for a while, we can immediately see why it is 0. The reason it's 0 is because beta, gamma, and alpha all create and destroy different kinds of particles, so all these operators commute with each other. So nothing stops me from moving gamma, let's say, over here next to this vacuum, where it then annihilates the vacuum, gives me 0. Or I could commute alpha to this side and get 0, or I could commute beta over here. There are all these particles, all these operators I could move next to the vacuum states here and get 0. So there are sort of many ways it can vanish, okay? Now what this teaches us is that if we want to get a non-zero result, I have to stop gamma from being able to be moved over here. That means there has to be a gamma dagger in between somewhere. Similarly, there has to be a beta dagger somewhere in between to prevent me from moving this guy over here, and there has to be an alpha preventing me from moving this over here. So that tells me the kinds of terms that I need that where I won't get 0. I need all 3 of those things, okay? And so we can see, okay, so this term is 0. Now we want to go to the next order, the IG term, and we can see what we need because we need one of each of these operators. We need a beta dagger, a gamma dagger, and an alpha. So the alpha is obviously going to come from here. Where is the beta dagger term going to come from? The beta dagger term will come from here, and the gamma term will come from here, if you look at the definitions. So the next term we have is plus IG, then we have our d4 x, and then we're going to have a momentum integration over the mass shell for each of these guys. So we have a dk1, a dk2, a dk3, okay? And then we're going to have our beta and gamma terms on the left, right? We'll have a beta, let's say vacuum, beta of Q1, gamma of Q2, and then we'll have our, from this guy, let's say we'll have our beta dagger of Q1, sorry, K1, okay? So K1 is going to be an integral from, let's see, I guess this guy right here, okay? And this is going to come with a, this is going to be actually a negative frequency term, so we'll have a plus ik1 dot x, okay, from this guy right here. From this guy right here, we're going to pick up a gamma dagger, okay, and that will also be with an ik2, so a gamma dagger of k2, e to the ik2 dot x, okay? And then we want to get the alpha dagger from here, okay? And that will be an alpha dagger of K3, and that will be an e to the I K3 dot x. Okay, so actually I think I have the positive and negative frequency backwards. So beta dagger here, this should be, yeah, these are both minus. Okay, I think if we do this thing carefully, these things here should be minus. No, other way around, sorry. These are positive here, and this one is negative. Okay, so if we expand these things out, we will get that. Okay, and then I still have to put my alpha dagger of P acting on the vacuum state. Okay, so this is the only term at order G that can contribute. Then I don't know what happens at higher order, so I could have some order G squared corrections. Okay. Okay, so now with my previous logic, I could say, all right. What stops me from, for example, moving this gamma, okay, all the way over to where it hits this? Well, I can move it past the beta, but here I have to move it past the gamma. moving it past the gamma means I get a factor of I get a term proportional to the commutator, but the commutator just gives me a delta function between Q2 and K2, right? Similarly, if I'm trying to get the beta over by here, I have to move it past this beta dagger. That will give me a term with a Q1 beta 1 delta function. And similarly, this alpha guy, sorry, let's say, whoops, this should be alpha, not alpha dagger. Sorry, this is alpha. This alpha term, moving it past this alpha dagger, will also give me a delta function of pk3, okay? So actually, this is just going to give me a whole bunch of delta functions, okay? So all right, so now let me erase this stuff up here, okay? I'm still calculating this S matrix element, and now the leading term I have is this IG, and I have all of these integrals here, dk1, dk2, dk3, okay? Oh, something, by the way, something I forgot to mention here is that this K1 is over the nucleon mass shell, so I should probably put a little m here to remind myself that this is the nucleon mass. K2 is also over a nucleon, so this is little m. K3 is an integral over the meson, capital M, right? These have different, different masses for their mass shell. So we have m, little m, big M, okay? So here are my integrals, and then each one of these combinations like beta, beta dagger is just going to give me one of these delta functions, okay? So I am just going to get, I'm going to get a Q1, K1, a Q2, K2, and a P, K3, okay? Those just come from the terms that I get by multiplying all these things together, okay? And then I have a, right, and then I have the exponential terms, right? So I have e to the ik1 dot x, e to the ik2 dot x, and e to the minus ik3 dot x. So I have a factor of e to the I k1 plus k2 minus k3 dot x. Okay? All right? So I have 3 momentum integrals and 3 delta functions, so I can just do all of the momentum integrals immediately. Okay? And here I have order g squared terms. This is just the leading term. So I can do all the momentum integrals. What do I get? Ig. K1 just turns into Q1, etc. And so I just have d4x, okay? And then all I have is left is just this exponential, e to the I, now Q1 plus Q2 minus Q3 dot x, okay? And this is another integral that I know how to do. This is just a delta function. So this is Ig 2 pi to the 4th delta 4, this is P, sorry, Q1 and Q2 are the final momentum, P is the initial momentum, so I get a P here. So I just get a delta function, P minus Q1 plus Q2, okay, times Ig, okay? So after all the dust settles, my first S matrix element, okay, that I've calculated in this course, is just I times G times a 4-dimensional delta function, okay? Now, maybe the 4-dimensional delta function is reasonable, right? Because it says that this process is, this amplitude is non-zero only if we preserve both energy and momentum, which is certainly a reasonable thing, okay? But it's very confusing how to physically interpret this, right? Because remember that we want to find something physical, we want to find a probability, right? And the probability will be proportional to this S matrix element squared, right? And while delta functions don't scare me, squares of delta functions do. What do I mean by the square of a delta function, okay? And so we're going to have to now try to understand how we interpret this. And the claim is that this divergence, this delta function squared divergence, is related to the fact that we're working with an infinite volume and an infinite time. So to see what's going on, we're going to have to go back to finite volumes and finite times. So that's what we're going to do now. So to regulate the large time and large volume, we'll put our theory inside a box, inside a spatial box of size L, and we'll also limit the time extent by a time t. And so we'll do that by imposing boundary conditions on our fields, where if you move the fields, if you translate the fields either by a spatial amount L or a time t, you get back the original fields. Here E hat is X hat, Y hat, or Z hat. So we're basically putting the theory inside a cube like this. And the point of doing this is that when we do this, now the states are discrete. We know how to count them. Delta functions will be replaced by Kronecker deltas, which we can square without any mystery. So for example, the momentum states will be multiples of 2 pi L, basically 2 pi L times a 3 vector whose components are integers. So the states are just, the momentum eigenstates are just labeled by these integrals. And now if we can define states for these discrete things, and we will call those, denote those states, they'll be 3 vector states, and we'll put little v's here. V here is just the spatial volume, L cubed. And these will just remind us that we're using states in this discrete normalization here. And this will just be a Kronecker delta, P comma Q. Okay? So this Kronecker delta is 1 if these two P's and Q's are equal, and it's 0 otherwise. Okay? And that makes sense because we have discrete states. Okay? Now, of course, we're doing this because we're interested in eventually taking V goes to infinity and T goes to infinity. So let's look how that continuum limit works. One thing we want to be able to do is to sum over momenta, right? And that will be related to an integral over momenta. And from this equation right here, you can see that the integration measure is d cubed p over 2 pi cubed, and you also get a factor of the volume, like this. Okay, so this is how you turn momentum sums into momentum integrals. And the other thing that we'll want to do is we'll want to take Fourier transforms. So if we have d cubed x e to the I p minus q dot x, okay, we integrate over the volume. Well, in finite volume, it's clear that this is equal to the volume times delta of p q, right? Because this integral vanishes if the p's and q's are not equal to each other. If they're equal to each other, I just get the volume, right? And now if I take the continuum limit, on the other hand, of this, I know that I get 2 pi cubed, delta cubed, p minus q. Okay? So this tells me how to identify the continuum delta function with the Kronecker delta. And you see that indeed you get these factors of v. Okay? All right? Okay, so this now lets us relate the discrete normalized state to the continuum normalized state, right? So if I look at what I just erased, if I look at PQ at finite volume, right, that is delta of PQ. But from the formula above, I see that in the infinite volume limit, that is related to 1 over the volume times 2 pi cubed, delta cubed P minus Q. Okay? And I know that this, so from this, I can work out what the relation is between the relativistically normalized states that I write my theory in terms of, and these discrete states, right? Because this in turn is 1 over v, and then I have a 1 over factor of 2 e p p q, where these things here now are my relativistically normalized state. I have to put in this factor right here so that, you know, I have to get the factor upstairs that I need to make this the Lorentz invariant delta function, okay? So what this tells me is it tells me the relationship between my relativistically normalized states that I use for real calculations, and these discrete states right here. There's a factor of 2 EP times the volume, the square root of that, between these states. Okay? Sorry, it's not very easily seen. Okay? Okay. All right, so this is the basic formula that connects the relativistically normalized state to these discretely normalized states. Okay? So now what I'm going to do is I'm going to be writing the S matrix elements of these discrete states, because for these discrete states, the S matrix is literally just a transition probability, right? Since the states are discrete, I know how to count the states. So, what am I doing? I am calculating, I would like to calculate the S matrix element, but now between states that are normalized with infinite volume. And what are these states? Well, the initial state is some, the final state here is some state of, let's say, m q's at finite volume, and the initial state is the state of n particles with momenta p in the initial in the initial state, okay? And then using my formula down here, I can relate this to the S matrix element in terms of the Lorentz invariant states that I actually use, right? And you can see that to write this, I'm going to get a factor of 1 over this square root for each initial state and each final state momentum. So I'm going to have a product over all the initial state momentum, and for each initial state momentum, I'm going to get a factor of 2 EIV, okay? And for each final state momentum, I'm going to get the same factor, 2 E final V. Okay? So this is a shorthand here. So I is an index. I'm also using it as a shorthand for the state here. But it should be clear what this is. This one, for example, is the product. I equals 1 to n, the number of initial state guys, times the square root 2 EPI times the volume. Okay, that's what this is. And similarly for that one over there. Okay, and then this is this is just the factor that goes between, and so this thing is then multiplied by Q1 through Qm S P1 through Pn. Okay, the normal S matrix element. Okay. Now, as we've just seen in our first example for decay, but in fact it's actually general, this S matrix element, Q1 through Qm, S, P1 through Pn, okay, that S matrix element will always have a momentum conserving delta function in front of it. So it'll always have the kind of form that we found, namely it will be 2 pi to the 4th, delta 4th, P1 plus Pn, let's actually write this as capital P initial minus capital P final, okay? It'll always be proportional to that, and the rest of it we're going to call I times M F initial, okay? So the coefficient here of this S matrix element we just call this, and this thing right here is a Lorentz invariant amplitude, okay? This is the Lorentz invariant amplitude between initial states I and F, and that's going to be the basic object that we're going to actually be computing, okay? And so here, it should be clear, P initial just means P1 plus Pn, and capital P final just means Q1 plus Qm, and these are the 4 vectors, right? And so just to make the connection clear, in the previous example, Mf initial was just equal to, drum roll please, G, right? Because before what we found is Ig times this, okay? So the Lorentz invariant amplitude, you can see, is an extremely simple object in that case, okay? But anyway, in general, it'll have this form right here. It'll be proportional to this, this delta function, okay? So, okay, if we put that in up here, how do we do that? Well, we're going to have to write this thing in terms of discrete normalized things now, right? Because we want to understand how to square this delta function in finite volume. And we can see that what this becomes, it becomes the volume times the time, okay, of a Kronecker delta between P initial and P final, okay? So this Kronecker delta is 1 if the initial and final 4 momenta are equal, and it's 0 if they're not, okay? Okay, so if we put all of that together, right, what do we get? I'm sorry, I'm going to erase, I'm running out of room, but if we put all that together, what do we have? We have that our finite volume matrix element is V times T times this Kronecker delta, P initial and capital P final, the total initial and final momenta, and then we have our factors, E initial, 2 E initial V, a square root factor like that for each initial momentum, a square root factor like this for every final momentum, and then finally we have our Lorentz invariant matrix element, okay? All right? So now it's written all in terms of discrete quantities, and so now we're just going to square it. So the probability to go from the initial state to the final state is now just equal to the square of this S matrix element. Okay? Because this is now a discrete normalization. There are no subtleties. This is just a probability, right? Okay. And so now we know how to square this. So we get V squared T squared. And the square of a Kronecker delta is just a Kronecker delta, because when it's 0, it squares it, you know, the square of 0 is 0, and the square of 1 is 1, so it's just a Kronecker delta again. There's no fear of squaring a delta function if it's a Kronecker delta. And then each of these product factors, instead of the square root thing, I just get a factor of 2 E initial V for each initial guy, and I get a factor of 1 over 2 E final V for every final guy, right? And then I get my matrix element squared. Okay? All right. Now what I want to do is I want to go back to the continuum now. Now that I've squared the amplitude, I want to go back to the continuum. Okay? And if I go back to the continuum, what will happen is I take Vt times the delta, that gives me the continuum Lorentz invariant delta function, but I still have one Vt left because this is Vt squared. So this here is Vt times 2 pi to the 4th, delta to the 4th, P initial minus P final, okay? And then I have all these factors, initial 2 initial V. For each final guy, I have a 1 over 2 E V, and then I have my matrix element squared. Okay? All right. Okay, so this here in the last step I've gone to the continuum. Okay? Now, in the continuum, I know that I have to, this right here is the probability to go to one particular discrete state. But in the continuum, I know that doesn't make sense. In the continuum, I have to integrate over a range of final states, right? Because in the continuum, any experiment has a finite resolution, okay? So I know that what I'm going to be interested in is I'm going to be interested in taking sums over final states, okay? And a sum over final states, if I look back at my normalization, that turns into an integral, okay? A product for each final momentum, I get a factor of V d cubed q final over 2 pi cubed, right? Okay? So to sum over final states, that's equivalent to summing over the q's, the final state q's, and for each q, this is the appropriate measure right here, okay? And so what this means is that I'm going to define a differential rate, d gamma, okay? That is a probability per unit time, okay? So this thing right here is going to be this measure right here, the product over f, v times d cubed qf over 2 pi cubed. That is the final state measure, right? And then I'm going to look at the probability to go from the initial state to the final state per unit time. So that this right here is a differential rate. Okay? All right? And if I look down here at the last expression that I derived here, I see that very nicely looking at a rate, a probability per unit time, absorbs the one and only time factor that I have. So now my expression becomes independent of time. That makes sense, right? And then let's write the rest of it out. Okay, so I have my factor here, my measure, 2 pi cubed, okay, for each final momentum. And then I have this factor here without the t, because I divided by t over here. I have a volume. I have my 2 pi to the 4th, delta 4th, p initial minus p final. And then I have these other factors here. So I have left over. I have, for each initial guy, 1 over 2 e v, and for each final guy, I have a 1 over 2 e final v. And then I have my matrix element squared. Okay? All right? So now we do see some nice things happening, because for each final momentum, I have this factor of v upstairs, but for each final momentum, I also have this v downstairs. So these v's all cancel against these v's. Okay? Furthermore, for every final momentum, I have this factor and I have this factor. So those nicely combine into the Lorentz invariant measure for the QFs. Okay? And so what do I get? I get a product over F, and then I get the Lorentz invariant measure, right, for each of these QFs once I combine this with this. Okay? And that now gives me, that takes care of this factor and this factor. Okay? Then I still have my delta function here, 2 pi to the 4th, delta to the 4th, p initial minus p final. Okay? And then I still have this volume factor here and all these factors here, which also include volume factors. So I have volume times the product over the initial states, 2e initial v, okay? And then my matrix element squared. Okay, so this is my formula for the differential rate. Okay? And this is a very nice formula. This is sometimes called Fermi's golden rule. Fermi first worked out this kind of way of understanding how do you interpret transition rates between continuum states in quantum mechanics. Okay? So one thing that you see is that, well, in general, these factors of volume are not canceling out. Okay? So you have to wonder whether this really makes sense in the infinite volume limit. All right? So let's look first at the case of decay. That's the case that we're actually, where we computed the S matrix element. So decay is the case where the initial state is a one-particle state. It's just one particle in the initial state, right? So that means that I only ranges over one thing, and so in that case, actually, this V does cancel that V, okay? So in that case, our differential rate can just be written as we have 1 over 2 EI, okay? And then we have our final state phase space factor, QF, from here, one of these for each guy. We have our momentum conserving delta function. Okay? And then we have our matrix element squared, and that's it. Okay? So very nicely for this, the volume factors actually do cancel out. Okay? And so this tells us that we get even in the infinite volume limit, there is a well-defined rate, differential rate for the particle to decay, and that's very nice. Okay. Notice that this thing is not Lorentz invariant, right? It sort of almost is. This is Lorentz invariant. This is Lorentz invariant. This is Lorentz invariant. But this is not Lorentz invariant, right? But then, when you think about it, a decay rate should not be Lorentz invariant. It's a rate, right? So there's time dilation. If you have, very famously, if the muon is moving close to the speed of light, it travels much, much further than you would guess by just naively taking its lifetime, rest lifetime times its speed. So that's Lorentz, that's time dilation. And that's exactly what this factor is. If we're in a frame where the momentum of the particle is very large, this suppresses the decay rate, so it means it lives longer. So this is exactly the time dilation factor that we needed to have from relativity. So this is a relativistically correct formula, which is very nice. Okay? Okay, you may be thinking that we're cheating by just looking at decays because the scattering, if we have two particles in the initial state, for example, scattering, the volumes don't cancel. We'll look at that case next lecture. Of course, that case works as well. Okay, but now let's sort of excuse me. Let's consolidate things a little bit. This factor right here, will appear in all rate calculations that we do, and this thing right here is basically the final state phase space, it's called. It's the fact that there's some volume element for each final state momentum. There's always this momentum conserving delta function times this product of Lorentz invariant mass shell integrals. And this thing right here we call the Lorentz invariant phase space with momentum P initial. So this depends on the total initial momentum, right, through this delta function. But other than that, it's just an integral over all of these things right here. Okay? And so we can look at for example, if we want the total decay rate, okay, right, it is just going to be the integral of the differential decay rate, which now is just going to be, and let's take the total decay rate in the rest frame of the particle. Okay, so that's a Lorentz invariant quantity. In the rest frame of the particle, what is the decay rate? Well, E is just the mass of the particle, so I get a factor of 1 over 2m from here. And then I just have the final state phase space with momenta P integrated over the matrix element squared. Okay? And this, of course, now this is all Lorentz invariant as it should be. Okay? Okay, so let's apply this to our toy model. Okay, in our toy model, we actually calculated this thing right here, right? What was it? It was actually just g squared. It was just a constant. Okay, so to find the total decay rate of the meson into two nucleons in that model, we just have to do this integral. We can actually pull out the g squared. Okay, so let's actually do that integral and thereby compute our very first physical quantity in quantum field theory. So the decay rate is just going to be g squared over 2m. This is the mass of the decaying meson. And now we have to integrate over the two-particle final state phase space. So this is d cubed q1, 2 pi cubed, 2 e1. Let's start this e at q1. And then we have d cubed q2, 2 pi cubed, 2 dq2. Okay, that's the measure. And then we have our delta function, 2 pi to the fourth, delta fourth p initial minus q1 plus q2. Okay? Okay, so we can immediately we have 4 delta functions here, so we should use those to do our as many integrals as we can. And we should also remember that capital P mu initial, the initial momentum, since we're in the rest frame, it just looks like this, right? The energy is m, and the 3 momentum is 0. Okay, and so we can use the d cubed part of this integral right here to do the q2 integral, right? So do the d cubed q2 integral, and what does that give me? It just tells me that q2 is equal to minus q1. because in the rest frame here, there's no 3 momentum here, right? So in the rest frame, vector q2 is just minus q1, okay? So then I can immediately do the q2 integral right here, okay? And what do I get? I get g squared over 2m. I still have the q1 integral to do, okay? Now this, there's the 2 pi cubed kills this 2 pi cubed. I'm going to have to leave over the 2 pi here. But I have this factor and this factor are left over. Because these momenta are equal and opposite, E of q2 becomes the same as E of q1, right? Because the sign of the vector doesn't matter. And so I get a 2 eq1. I get a square, I get 2 of those factors, okay? So now I've taken care of these factors, and what I have left over here is a 2 pi times the time delta function. And for the time delta function, I have to equate the 0 components of this, and that will tell me that m minus 2 square root q1 squared plus m squared is what has to be 0 according to the time delta function, the energy conserving delta function. Okay? Okay. Now I realize that, well, I can actually do this integral here because, well, here this simplifies a lot because everything is actually spherically symmetric, right? Nothing depends on the direction of q. It's only q vector squared that enters here. So I can just use spherical coordinates in momentum space here, and the spherical element is 4 pi q squared dq. I have my 2 pi cubed, and now this q right here is just an ordinary real number that goes from 0 to infinity. It's the radius in q space, okay? And then I have my 4, and this thing here becomes q squared plus m squared, little m squared. That's this factor here. Then I have my 2 pi. Now I have my delta, and it doesn't matter which way I write this. I can just write it like this. 2 times this thing here minus capital M. Okay? And now this is, again, the world's easiest integral because I have a single integral, but I still have one delta function here, right? Okay? So now there's a whole bunch of pi's and 2's and things that I want to collect. At least according to my notes, if you do that, what you should get is a net factor of g squared over 8 pi m. So just cleaning this up a little bit. Then we have the integral from 0 to infinity dq. And what is the integrand? Q squared over q squared plus m squared, collecting these various factors, times the delta function of 2 q squared plus m squared minus m. Okay, so that's just cleaning up the previous expression. Now, again, this is the world's easiest integral. We just have to evaluate the integrand when this argument of the delta function is 0. But we do have to be careful because there's not this thing, there's a non-trivial Jacobian factor coming from the fact that there's a function of q inside here. Okay? So, what does this delta function enforce? If we solve this equation right here, we can easily solve it. And this delta function right here enforces that little q is equal to 1/4 of big M squared minus, no, 1/2, sorry, big M squared minus 4 little m squared. Okay? That's just solving the equation that this is equal to 0. Okay? And what you see is that this makes sense only if m is bigger than 2m. And that's how it should be, right? This is the meson mass, and only if the meson mass is bigger than twice the nucleon mass is there enough energy in a meson at rest to even make 2 nucleons, okay? And if this is not satisfied, well then this is just 0 because this delta function is, the argument of this delta function never vanishes. So, yeah, this reproduces what we expect, right? Namely that energy is conserved, and so heavier things can only, you can't have lighter things decaying into heavier things, basically, okay? All right, so now if we do the integral, what do we get? We have this factor of g squared over 8 pi m, okay? And then we have to evaluate the integrand at this point, okay? So we have to evaluate q squared q squared plus m squared. But then we also get this factor, this Jacobian factor, okay? And what this is, I'll just write it down. I'll leave it to you to check that this Jacobian factor is actually this, square root q squared plus m squared over 4q. And all of this is supposed to be evaluated at this special value of q, capital M squared minus 4 little m squared. Okay? And yeah, and this is the Jacobian factor, okay, that comes from the fact that the delta function is non-trivial. So now, if you just do this, there's just a little bit of algebra, okay, and what you get, I claim, is the following. I get 32 pi m, okay, and g squared on top, okay, and then you get this factor 1 minus 4 little m squared over big M squared to the 1/2. Let me get rid of this. Okay, and here we go. So let us pause to admire this, because here it is. This is our first actual calculation of a physical quantity in a theory. This theory, the parameters of this theory were the coupling, G, was the strength of the interaction, and the masses, and there's some formula that depends on a combination of these. And this is supposed to be the total decay rate of the nucleon, excuse me, the meson into a nucleon-antinucleon pair in this theory. Okay, so let's look at this and see if it makes sense. What could we check? Well, one thing we could check is after all of this, we should still get the right units, right, at the very end of the day. So this is supposed to be a decay rate, right? A decay rate is a 1 over time thing. This is 1 over time. And so therefore, that should have mass dimension plus 1. It should have dimensions of mass to the 1. And if you look at this, lo and behold, it actually worked, right? Because G had dimensions of mass. So G squared over M has units of mass, and this is dimensionless, so it actually works, okay? Another feature that's kind of interesting here is notice that this factor right here goes to 0 as m, let's say, as little m goes to 1/2 big M. In other words, if we go towards the threshold, right, where this decay is just barely allowed, right, we need capital M to be bigger than, let me write the other way around, m goes to 2m, okay? So if these masses are getting very, very degenerate, then this factor is getting not degenerate. If big M is close to 2 little m, then this factor is getting smaller and smaller. So that's telling you that the decay rate is getting smaller, right? So, and this is suppressing the decay rate. And the way we can understand that is that, remember, to find the total decay rate, we have to sum over all of the final states. But when we have this relationship satisfied, if capital M is nearly 2 little m, then there are far fewer states to sum over, right? Because there are a limited number of states that actually satisfy energy momentum conservation. So we say that in this case, we say that the decay is phase-space suppressed. And this is a very important effect in a lot of cases. For example, the decay of a neutron is extremely suppressed because of factors like this, and that accounts for the very long lifetime of the neutron. Okay, so it's actually very important in our everyday lives. Okay, so that's it for now. Next time we'll talk about scattering.